Calculus students, now that we've talked about how to do parametric curves, doing calculus with parametric curves, finding slopes of tangent lines and concavity, area, arc length. All right, so we have a parametric curve for time -1 to 4, and our goal is to find the equation of the line that is tangent to this parametric curve when t is 2. As time varies from -1 to 4, we get this curve. Now we're interested in what happens when time is 2. We want to know the tangent line at that point. First, find where exactly is the point at time 2. So we're going to calculate what x of 2 is and what y of 2 is. So plugging in 2, for x we get 3 plus 2 cosine of 2. We could find a decimal for this, right? And the y-coordinate at time 2 is 5. To get the slope of the tangent line, normally we would use a first derivative. Well, we're going to do the exact same thing here. The slope of the tangent line will be found by doing the first derivative, which is dy dx, change in y over change in x. And when you're working with parametric equations, you can do the derivative of y with respect to t over the derivative of x with respect to t, and then plug in t equals whatever time you're interested in, time 2 in this case. Another way you could write this notationally is saying y prime of 2 and divide that by x prime of 2. In order to find that, we're going to have to find some derivatives first. So let's go ahead and find out what x prime and y prime are. X prime of t is -2 sine t, and y prime, the 6 will go away. This 2 here will drop down and multiply to that -1, so we have a -2 in front, a t minus 1, the new power is 1, and the chain rule outputs a 1. So we just get -2 times t minus 1. So to find the slope of the tangent line, we want to plug time 2 into these derivatives. So plug 2 into this t right here, and we get -2 up top. And the bottom, we plug in t equals 2 for that t right there. We get -2 sine 2, which you could simplify to 1 over sine of 2. All right, so there's our slope. x1 and y1, what we use for the x-coordinate of the point we're going through, and we use y1 for the y-coordinate. To create the equation, we just use point-slope form. Y minus y1 is equal to m times x minus x1. Y minus y1 will be y minus 5. The slope is 1 over sine of 2, and the x1 is, I'm going to put that in parentheses, it's 3 plus 2 cosine 2. So technically we're done, but let's go ahead and solve for y, and we'll call this good enough. Now when you graph this line, it's going to look like the tangent line. Just like that, I've graphed our tangent line. Let me show you something cool that you can do with Desmos now. I'm going to delete that, x1 equals, and then plug the capital T into the capital X function. Let's do something for y sub 1 next. Plug capital T into capital Y. Now we want to do something for the slope, little m equals, and then we're going to plug capital T into capital Y prime of capital T divided by, and we do the same thing but x. Then create a new line, and now just type in your general equation. Y minus y1 is equal to m times parentheses x minus x1. Now what's cool about this is since I've kept everything in terms of the functions and of capital T, and when I hit play on t, you're going to actually see the point move and the tangent line change with it. So we're animating now a tangent line as the point is moving around. Find all values of t in this interval where the given parametric curve has a horizontal tangent line. Then find all values of t where it has a vertical tangent line. Well, visually you can see that this curve is going to have a horizontal tangent line somewhere around up here. And then there's going to be a vertical tangent, somewhere in this area. Since your slope is equal to y prime over x prime, if you want your slope to be 0, then you want the top to be 0. If you want your slope to be undefined, which is true for vertical lines, you want your denominator to be 0. Let's start with the top one, y prime. It was -2 times t minus 1. We set this equal to 0 and we solve for t. You can divide by the -2, that doesn't matter. And we confirm that when t is 1, y prime will be 0. And so this is the time where we're going to have a horizontal tangent. If you want to do the vertical tangent, then you set the denominator derivative equal to 0. X prime of t is equal to -2 sine t, and we want this to be equal to 0. This just means that sine of t has to be 0. Well, sine will be 0 at 0 and all multiples of pi. So t could be -pi, or 0, pi, 2 pi, etc. But we only want to keep the t's that are in this interval right here. But 0's in there and pi's in there, and then 2 pi is outside of it. So we just want to keep t is equal to 0 and pi, which makes me realize that there's an obvious another case over here, right, where the tangent line is vertical. And this one here occurs when t is 0. This vertical one will occur when t is pi, and this horizontal one occurred when t was 1. And the graph started when t was -1, and it ended over here when t was 4. When t is 0, notice that the tangent line disappears. That's because x prime is 0 at this location, and so your traditional slope is undefined, so we expect to see no line when t is 0. Otherwise, we see lines. When t is 1, we had a horizontal tangent, and the other t is when t was pi, in which case there is, again, no line. The next slide, let's do second derivatives. find the value of the second derivative when t is 2. And we're talking about the second derivative in the traditional sense, which is a rate of change of the rate of change of y with respect to x. When time is 2, first of all, we're still focused on the same point right around here. And if you recall what second derivatives tell you about the shape of a graph, if a second derivative is positive, you expect to see concave up. And if a second derivative is negative, you expect to see concave down. Well, in this portion of the graph right here, this is concave down. So we expect to get a negative second derivative at this time. And here's how you calculate it. The second derivative is the derivative of the first derivative. So when I say d squared y over dx squared, this is Leibniz notation for doing this. The derivative of the first derivative of y. Okay, well, we get the first derivative is going to be a function of t because, well, let's take a look back. Oh, I did not write down what the derivative was in general, so let's take a moment and do that. In general, the derivative of y with respect to x is simply you put the y prime expression over the x prime expression, and then simplify if possible. This one goes to a nice t minus 1 over sine t. You'll notice that the first derivative is just a function of time again. When we go to the second derivative, the thing that's right here is just another function of time. So to do a second derivative, we are going to do the derivative of our dy dx with respect to t, and then divide that by dx with respect to t. I'm going to just copy dy dx that we did up here. Okay, so there's the first derivative. And then to do the second derivative, we do a derivative of this expression right here. And we do that with respect to time. And then we divide that by a derivative of x again with respect to time. To do the derivative of the first derivative, we need to do a quotient rule right up here. So do the derivative of t minus 1 is 1 times the bottom minus the top times the derivative of sine t, which is cosine t, all over sine squared. And we divide all of that by the derivative of x with respect to t, which was a negative 2 sine t. And then we simplify this a little bit. You can think this is being over 1, and then we're going to invert and multiply. And so in the end, this winds up looking like this is an expression that tells us what the second derivative is as a function of t. All right, so now what's the second derivative of this curve is going to be equal to this expression right here. And we want to evaluate it specifically when t is 2. So we plug in 2's, then we just get sine of 2 minus, and plug a 2 in for that t. That gives a 1 in front of that cosine, so it's just going to be minus cosine of 2 all over negative 2 times sine cubed of 2. The negative suggesting that at this time the curve should look concave down in our traditional sense of y against x. All right, arc length. So let's say we have some sort of curve and it starts at a certain time and ends at a different time. The question will be, well, how long is this curve? We grabbed a little portion of this, we zoom in and we approximate how long a portion of it is by doing Pythagorean theorem on the change in x and the change in y. And the portion I'm talking about is the curve that's bending, it's not straight line. So you can see why the straight line hypotenuse is really just an approximation. But the approximation becomes more and more accurate as you cut this curve up into smaller and smaller pieces. And so as the number of pieces approaches infinity, we get an exact answer through the integral. Looking at this picture here, then the horizontal would be a change in x and the vertical would be a change in y. We're calling the ds, right, the diagonal there. And Pythagorean theorem says that ds squared should equal dx squared plus dy squared. And then I can divide everything here by dt squared. ds squared is equal to times the dt squared. And then take the square root of both sides and we get ds is equal to the square root. Now this is really just dx over dt squared. So in other words, it's the derivative of x with respect to t being squared. And here's the derivative of y with respect to t being squared. And then you square root the dt squared over here, you just get it in dt. And so the actual arc length, it's going to be an integral from time a to time b, and then you put this ds in there. And this is our arc length integral that we're going to work with. We're going to do everything in terms of t, and it's going to give me the length of that curve up there from time a to time b. So let's start with this familiar one that we have here. We'll get it set up by hand, but then we'll use technology to finish it out. So the length of this curve will be an integral from time 1 to time 4, and then you do the square root of x prime of t, and that's going to be squared, plus y prime of t, and that's going to be squared. Then you do the square root of all that, and then you have your dt at the end. And so in this case, the derivative of x was negative 2 sine t, and that needs to be squared, plus the derivative of y was negative 2 times t minus 1, that needs to be squared. And all of this is inside of a square root, and then dt. This is one that I don't expect you to do by hand. L is equal to int from 1, was it 1 or negative 1? It should be negative 1. Negative 1, negative 1. Okay, lower limit will be negative 1, upper limit will be 4. Then we do a square root. And instead of typing in the actual derivatives, I could just say capital X prime of t. Inside these squares, you put the derivative of x and the derivative of y. And since we've already typed them in up here, right, those are the two functions in question, we can actually have Desmos just say x prime of t and y prime of t. All right, the length of this curve is about 15.26 units. So meters or feet or inches or whatever the units of measure are. Here's another one. This one, notice that I don't give a range of t. We just have x equals cosine 2t, y equals sine 4t. We're interested in finding how long this bow tie shape is. So we're going to have to do a little bit of investigation to figure out the time interval where this draws itself. And make sure you pick a time interval where it draws itself only once. So there's our bow tie shape. We're trying to find out how long that is. Let's first figure out how it draws itself. Let's start at time 0. Put a capital T back in this position. Just make that start at 0 as well. And let's just go up to 10 just to see. At time 0 it started there, and it draws itself by the time you get to right here again. So somewhere when t is around, probably pi is my guess. Let's go ahead and put pi as an upper limit and play this. From 0 to pi is when it completes itself. Let's pause this and park that at pi. Let's just do our integral down here, and we want to integrate from 0 to pi. And there's going to be the length of this curve, about 9.43. All right, so in our notes, we discovered that the time interval was 0 to pi to draw itself once. And the arc length is an integral, therefore, from 0 to pi. The square root of the derivative of x is going to be negative 2 sine 2t, and that's going to be squared, plus, and now let's do the derivative of y. It's going to be 4 cosine 4t, and that's going to be squared. And then we take the square root of all that, and then we do a dt. And when we type this in, we get approximately 9.43 units. All right, so this formula is really easy to use, especially when we're just using technology to do the integrals. But let's do one here that we can actually manage without technology. Here the time interval was given, and we have the x and y functions. The length of this curve that you're seeing in this image will be an integral from time 0 to time 1. It'll be the derivative of x, which is 4, and that needs to be squared, plus, and then the derivative of y, which is just t, and that needs to be squared. And then all of that is inside a square root dt. So in other words, it's the integral from 0 to 1, 16 plus t squared radical dt. All right, this is an integral for which we can do trig substitution. This is a sum of squares, so I need to let t be equal to 4 tangent of some new variable. I'll use u, which means I need to change the differential. dt is going to be 4 secant squared of u, du. Let's leave these as t limits, and I'm going to go back to t's before I do my evaluation. We have an integral from t equals 0 to t equals 1. The square root of 16 plus, when I change this t to 4 tangent u and then square that, I'll get 16 tangent squared. And then the dt is 4 secant squared of u du. Or I can factor a 16 out and take its square root separately, and that becomes a 4, combining with that 4, making a fresh 16, which I'll pull all the way up. And then what's inside that radical will be 1 plus tangent squared, which is secant squared. Using Pythagorean identity, square root that becomes secant, and then multiply by this secant squared, and we should wind up with this integral. Then the antiderivative secant cubed, if you recall, this was one we just had memorized, is the average of the derivative and antiderivatives of secant. By average, we're going to divide by 2, and then the derivative of secant was secant tangent plus, and the antiderivative of secant was natural log of absolute secant plus tangent. We're going to evaluate it from 0 to 1. Make sure these are t's, right? So we're going to have to do back substitution. So that's where up here we're going to make a reference triangle. We know that the tangent of u is t4ths, and tangent is opposite over adjacent. Pythagorean theorem will give me this side. It's the square root of leg squared plus the other leg squared. This is a reference triangle to convert these secants of u's and tangent of u's back into t. All right, so the 16 over 2 is an 8. All right, let's do secant of u. Secant of u is hypotenuse over adjacent. There should be no square right there, by the way. Radical 16 plus t squared over a 4. The tangent of u is t over 4. And then now that it's back into terms of t, we can plug these in. Okay, let's plug in the 1 first. We get a radical 17 over 4 times a 1/4. That's just radical 17 over a 16. Plus natural log, absolute value, radical 17 over 4 plus 1/4. That's just going to be 1 plus radical 17 all over a common 4. And then minus 8 parentheses. Now let's plug in 0. The 0 for that t is going to zero out that whole first part, so that's just gone. And then the 0 over here, well, that will go away. This will become a natural log of radical 16 over 4, which is 4 over 4, which is 1. So we just get a natural log of 1, which itself is 0. That whole right side zeroes out when you plug in 0, which means I can now distribute my 8, and I get the following answer. 8 over 16 is a half times radical 17 plus 8 natural log of absolute values aren't really needed because this is a positive number here. 1 plus radical 17 over 4. There it is. Just looking at the image, you could guess approximately how big of a number this actually is. It's going to be more than 4, but not nearly as long as 5, and something close to 4. Okay, last topic is areas of parametric curves. Okay, we have a new example to work with, so let me type that into our Desmos. We're trying to find the area underneath this curve, right, the shaded region here. Notice first of all that it starts at this location but it ends here, and vertically those aren't aligned. In fact, if our objective is to figure out the area of the shaded region, then I really don't care about when it doubled underneath itself. This part of the curve I don't even care about. What we do need to do is figure out the time where this happens, and just figure out the amount of area under this portion of the curve. Try to find where the tangent line is vertical, which means solve where x prime is 0. So you would find the derivative of x. X prime of t is negative 2 sine, and you set this equal to 0 and solve for t, and keep only those answers that are between 1 and 5. Right, this means that the sine of t has to be 0, right, which means t could be lots of things, negative pi, 0, pi, 2 pi, etc. But the only one that's in this interval is pi. So this occurs when t is pi. After pi, I don't care about that. All right, in general, if we're trying to find the area underneath the curve, we would do a whole bunch of vertical strips and then do an integral, and we get an exact answer. Our basic structure when we're using vertical strips to figure out the area under a curve is area is equal to, is that we're going to integrate the height of each strip is given by the y-coordinate, and the thickness is given by the dx. So it's going to look like y dx. And then we would integrate between two x coordinates. And since the bottom of the region here is y equals 0, we don't need to do top minus bottom. Just one function here because we're going from the x-axis up to that curve. So that's our general approach to finding area when we're using vertical strips. And this formula simply gets adapted to be calculated in terms of t. So it's going to wind up being an integral from t equals a to t equals b. And not the same as those a's and b's, right? Let's just leave that off. Here's our general structure. You replace the y with y of t, but this is the derivative of x. So you replace that with x prime of t and then dt. So here's your basic approach for finding area, although it's going to be problematic in this case for a reason that we'll see here in just a moment. So the starting time is equal to, we are doing 1 to pi. Replace y of t with this, right? And then you replace x prime with the derivative of x, which we've already done, it's right there, and then dt. To do this by hand, we would need integration by parts, which we could do, but I don't want to take the time to do that. Let's use Desmos to do this. Okay, so capital A will be our area, is equal to an integral from 1 to pi. Then we put capital Y of t here, and then times, and capital X prime of t, and then after that, the dt. Okay, notice what it gives us, negative 12.8. First of all, let's see what a reasonable answer might even be just looking at this. Right, each of these blocks is 1 by 1. It's area of 1. So we can count the blocks and then make predictions about how much area we expect to see. Right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, most of an 11th. And then these pieces put together, maybe this piece and this piece make around 12. So I'm expecting somewhere between 12 and 13 just by looking at this. This is giving me negative 12.8. So the number looks about right as far as area is concerned, but it's negative. Let's talk about why that is. The reason this is negative is because on this interval from 1 to pi, that the graph is drawing itself backwards. So there's several ways to fix this issue. This function x prime is negative on this interval because this curve is drawing right to left. That means x is decreasing. If you were to graph this function on this interval, you would see that it's below the x-axis, where this part is above the x-axis because on this interval, all the y's are positive. They're all up here above the x-axis. So this function's positive on the interval, but this function's negative on the interval. When you multiply a positive and a negative, you get a negative function on this interval. Therefore, when you integrate a negative function from a lower t to a higher t, you get a negative answer. The ways to fix this, you could put x prime in absolute value. Or, knowing that the graph is drawing itself from right to left, you could simply negate x prime. In other words, you could solve the issue by just making that a positive instead. The way to do that over here, though, is I just need to put a negative in front of that times the negative of x prime. That gives me a positive answer. We can also fix the issue by integrating it backwards, right? Just leave it the way it's set up and integrate from pi to 1. If you flip these around, put pi at the bottom and 1 at top. This is traditionally not the order in which you do integration when you're trying to find areas, but in this case, this rights the ship. If your curve is above the x-axis, the y here is just going to be y, because y is positive, you don't need to absolute value it. But the x prime is the trickier part. Is the curve being drawn right to left or left to right? If it's being drawn left to right, then x prime is positive, and you should get a positive answer out of this. But if the curve is being drawn right to left, then x prime is going to be a negative expression, and you want to negate that. A way to just be safe is just to throw this in absolute values, and this will give us an answer. So I can get rid of those parentheses and put an absolute value around that instead. In our integral over here, I got the x prime in absolute values, and it gives me the positive answer that I'm after. So you do have to do a little bit of thinking about when you're setting this up to ensure you get a positive answer. Don't forget we're finding an area, so these are square units. Same curve, but we're going to find the area under the lower portion. Okay, we know the curve ends right here when t is 5, and we know that this portion of the curve was when t was pi. So we're only interested from pi to 5 right now. And the curve is being drawn from left to right for this portion. So we still set up an area where all the vertical strips are all dictated by the y-coordinate. So the height of each vertical strip is that, and the width is dx. And we adapt this to be in terms of t. So we go from t equals pi to t equals 5. We replace y with its function of t, which is 6 minus t. And we replace dx with its derivative, which is negative 2 sine t dt. And when we do this, so without the absolute values, we'll get a positive answer. With the absolute values, we also get a positive answer, or the same answer. The reason why the absolute values don't matter in this case is because on this interval, the graph is being drawn from left to right, which means that the x prime, this function here is positive on this interval. And that's obvious from this image because the graph is drawing itself from left to right. X is increasing, so x prime is positive. So the absolute values aren't needed here, square units. But if you just want to be safe, you can just keep x prime in absolute values and you'll be safe. Now, the only trouble with these absolute values is when it comes to integrating by hand. If we're using technology, the absolute values is not a problem, but we haven't really learned how to integrate when there's absolute values at play. And so that's why the technology is helpful to ensure that that happens. Or you can look at the situation and decide, okay, in this top case here, x prime is negative. So instead of using absolute values, I can change the sign of x prime and now integrate this by hand using integration by parts. And in this case here, I would not even use absolute values because x prime is positive because the graph is drawing itself left to right. If I was doing this by hand, I wouldn't even write these absolute values. I would just leave it as you see it. Keep that minus sign there. This minus sign doesn't mean that this function is negative because sine of t is negative when t is on this interval. Therefore, negative 2 times sine t is positive. So don't get rid of that minus sign. Integrate this exactly as you see it using integration by parts, the table method, and you would get this positive answer. Finally, what if I want this portion right here between the curve and the y-axis? Well, in a case like this, sometimes it's helpful to use horizontal strips. We want to find the times where it crosses here and here. In other words, we're trying to find the times where x is 0. We take this and we say, hey, when is x 0? Not x prime, but x. So we solve this equation. Subtract 1, divide by 2, so we get cosine of t is equal to negative 1/2. There's a t in the second quadrant where this is true, and that t is 2 pi thirds. And there's a t in the third quadrant where this is true at 4 pi thirds. And then there's more, but as far as being between 1 and 5, these are the two limits. So t is 2 pi thirds, and down here it crosses again at t equals 4 pi thirds. Now there are a variety of strategies you could do here to find this area. I'm going to use horizontal strips just to illustrate doing that. But you could find out how much area is under the upper curve, like here, and then remove this area right here underneath that using vertical strips. But just for variety's sake, let me show you what the approach would be if I thought horizontal strips. Your basic setup for doing a horizontal strip area integral, you figure out how long a horizontal strip is, which has to do with x coordinates, and then the thickness is the dy. However, on this time interval, all the points on this curve all have negative x coordinates. So the x coordinate itself is going to produce a negative length. But if you do right minus left, it looks like you're just going to integrate negative x. So if I want a positive answer out of this, I actually have to integrate negative x here. Also notice that y is decreasing because this graph is drawing this way as time increases. So y prime is also negative because the y's are going down. So I would need to negate this one as well if I want to get a positive integral out of this. Or you could fix these issues by just absolute value of the x will guarantee we have a positive length, and then absolute value of the dy will guarantee we have a positive function there as well. Or if I omit both, this is a negative function, this will be a negative function, and we're going to wind up with a positive result. And so I could be totally absent-minded and not be thinking about any of this and just happen to turn out a positive answer when I set up the integral. Well, anyway, we're going to integrate from time 2 pi thirds and stop at time 4 pi thirds. We're going to replace x with its x function, so it's 1 plus 2 cosine t. And then the dy gets replaced with the y prime. So dy is just negative 1, and then we have the dt. Now again, on this interval, the values of this function are negative, and negative 1 is negative. So it turns out when you multiply these two functions together, the result here is going to be a positive function, so you're going to get a positive answer out of this without doing anything. This one we could do by hand, so why not? I'm going to distribute this negative first, and then integrate. So we have a negative 1 integrated is negative t. We have a minus 2 cosine t integrated is minus 2 sine t. And we're going to evaluate from 2 pi thirds to 4 pi thirds. For time's sake, I'm just going straight to the Desmos. All right, and we get that positive answer, 1.3697. And this would be, again, square units. And right what we expected, right? More than 1, but not quite 2, just looking at it.